Hello everyone, it's Benny, and in this video, we're going to be talking about some of the mathematics that go into normal mapping. Because, you know, all this lighting detail that you're seeing in this texture, it's not just coming from nowhere, there's some math involved. So, we're going to discuss some of the math that goes into it, and some of the math techniques that can actually help you get a lot better quality out of normal mapping than you could otherwise. So, yeah. Let's go ahead and dive in and get started. So, I'm going to start off by talking about tangents. Where do these magical tangents come from? How do you calculate these things? And well, there's a little bit of a trick to it. So let me try and explain. Let's say we've got our normal map. Looks something like this. And you know, it's defined all our normal vectors as well, vectors like this. And at least in the normal map space, 3D stuff looks sort of like this, where the x-axis of the texture sort of represents the x direction of the normal, the y-axis of the texture represents the y direction of the normal, and of course z is coming straight at us. That's sort of the direction it's representing in this texture. Alright? But, of course, we have to access this texture somehow. So, all our triangles have texture coordinates. There are points in this texture space defined by the y-axis, which in texture space is usually called the v-axis, and the x is usually called... In texture coordinates, the x-axis is usually called the u-axis, and the y is usually called the v-axis, just to distinguish it from 3D space, so yeah. It's usually some uv coordinate, which looks something like this. And of course that's part of a bigger triangle, which is defined by some other vertices. Here's the thing. What direction is up in this normal map? It's coming right at us, right? I already said that earlier. Now what's the tangent? It's the direction that's to the right of the normal. Well, I don't know about you, but the u-axis right here, that's looking pretty right to the normal to me. And the bitangent, which is, we don't explicitly define it in the vertex, but we still use it later on. We calculate it from the normal and the tangent. It's right here, and that looks suspiciously like the v-axis. So, this is sort of the trick. The trick is just realizing that we already have tangent space defined in texture coordinates. Because, well, in texture coordinate space, the x-axis is the tangent because it's tangent to the normal in this space, and the normal's directly up. Furthermore, we actually have a copy of our triangle defined in tangent space, because that's what the texture coordinates do. They're defining all these different edges, the whole triangle, all these vertices, in tangent space. So let me put it this way. Let's say this is one of our edges. You know, we take two of the vertices of the triangle, we subtract one from the other, boom, we get an edge. Cool. So what? Well, there's an interesting bit of mathematics here. Because a line in 2D space is generally defined with some x and y coordinate, or since the texture space, some u and v coordinate. So we got some delta u and delta v that represents the edge. Yeah, so what? Well, the delta u is defining something along the x-axis, and the u is the tangent in this space. And the delta v is defining along, well, the y-axis, and that's the bitangent in this space. So we've effectively defined the edge in terms of the tangent and the bitangent. And if we have a definition of what the edge should look like based on the tangent and the bitangent, well, that relationship should also hold up in 3D space. We should be able to define our 3D edges in terms of the tangent and the bitangent by these exact same ratios here. So, yeah, this delta u, if we multiply the 3D tangent by it and add that to this delta v times the 3D bitangent, that should give us the 3D edge. And that's sort of the mathematical trick. If you can get your head around that, you've pretty much got normal mapping and tangents and bitangents and whatnot down. So let's look at it a bit more mathematically. So, let's say this is our triangle, and our edges of the triangle are defined as E1 and E2. And this is our texture coordinate space, and the edges in our texture coordinates are S1 and S2. Now, based on what we talked on before, we can define edges like this. We have our 3D tangent and our 3D bitangent, t and b. If we multiply t by S1's x value and the bitangent by S1's y value, that should give us the edge 1, based on, because, well, in texture coordinate space, S1 is defined relative to the tangent and the bitangent, because that's, well, the tangent is, again, equivalent to the u-axis in texture coordinate space, and the bitangent is equivalent to the y-axis in texture coordinate space, or, well, you know what I mean. So, look at the equations here. If you've taken some algebra, you might notice something. We know what E1 is. We can calculate that by subtracting vertices. We know what S1 is. We can calculate that by subtracting vertices. Same thing for E2 and S2. We can calculate all those by subtracting vertices. The only variables we don't know here are the tangent and the bitangent itself. But we have two equations representing a relationship between the tangent and the bitangent. If we have two unknowns and two equations, that means, yes, we can do some algebra and calculate the tangent and bitangent. So that's all the sort of trickery involved in figuring out what the equation should be. Everything from here on out is just algebra. So let's expand these out. We've written them out in terms of their individual components, so E1, X, Y, and Z, this blah blah blah. Same thing, except just written out in terms of the individual components. And rather than S1x and S1y, I've gone ahead and done delta U and delta V1. So yeah, just, I don't know. I thought that might make it look a little clearer for some reason, so there you go. So, yeah, representing the exact same thing, except with that. But, if you do write it out like that, it makes it really easy to write this out as a matrix. So, I've got all my edges, they're equal to my delta U, delta V, the difference in the texture coordinates, and whatnot, multiplied by the tangent and the bitangent. And at this point, the algebra to find what the tangent and bitangent should be is really easy. If you multiply both sides by the inverse of this UV matrix, well, you get something that looks a bit like this. You get the inverse of the UV matrix times the edges is the tangent and the bitangent. And that's the math, really. If you want, you can go ahead and expand out the UV matrix so it looks something like this. So the tangent and the bitangent is 1 over this, not going to speak all that out, but yeah, times this new matrix, which is delta V2, negative V1, and delta negative. Oh, you can read it. What am I doing? All that multiplied by that. And again, all that's doing is just actually computing the inverse of this matrix and then writing that out instead. So yeah, that's another way you can write it out, and that's a little bit easier to actually write this out in code if you're coding this out, but yeah. And that's it, folks. That's the actual mathematics involved in calculating the tangent and the bitangent. It's just doing a little bit of matrix math, realizing that relationship between the texture coordinates and the tangents, and there. Now, even if you know the mathematics of calculating the tangents, there is a little bit of a trick in actually applying it, so I'm going to do a very brief code segment here where I show you how you would implement calc-tangents in an actual OBJ loader. So, right now I'm in my 3D game engine, the one I made in the 3D game engine tutorial series, and what I'm going to be doing is I'm going to be taking the OBJ loader in that 3D engine, and I'm going to be adding some calc-tangents. So, yeah, I'm going to copy the calc-normals function in index mesh and rename it to calc-tangents because, well, that's what we're doing now. And the math ends up being very, very similar. I'm going to comment out the normal code for now, but yeah. So, we've got, actually V1 and V2 are the edges, so I'm going to rename those to edge 1 and edge 2, just to be a little bit more consistent with the mathematics we wrote out. And the next thing we need, if we remember the math, is we need the delta U and delta V, because that's all part of calculating the tangent. Yeah, of course, that's what I'm doing. So, I'm just going to write them out just like I had in the equations, delta U1, and that's very simple. I'm going to say text chords get I1, wait, yeah, I'm going to subtract, dot get x, and I'm going to subtract I0, because that's what I'm doing with edge 1. That's I1 minus I0. Edge 2 is I2 minus I0. So I'm going to do the same sort of thing here. For delta U1, that's going to be like that. And delta U2 is going to be I2 dot get x minus I0 dot get x. And yeah, I'm going to do the exact same sort of thing for V1, except for... yeah, for V1, I'm going to do the exact same thing as U1, except dot get y. And V2, similarly, is going to be I2 dot get y minus I0, rather than, well, you know, before. And there. So I've got pretty much all the variables I need set up. But one thing I am going to do is I'm going to calculate that inverse beforehand, just so we're not rewriting that over and over. So I'm going to call the variable f, just because that's, I don't know, it's something to call. I don't know a good name to call that, so yeah. If you can think of a good one, let me know, I guess, but I don't know, couldn't think of one. And let's see. And that was 1 over, if you remember, delta U1 times delta V2 minus delta U2 times delta V1. And great. So, finally, we can calculate the tangent. The tangent, in this case, is going to be new vector 3f. I'm just going to initialize to nothing to start off with. Because, well, really just because I want to set it individually, kind of like this, so yeah. And there. So I got the tangent. And I'm going to set the x to, well, f times sort of the expanded matrix thing. And what on earth is the expanded matrix thing, you might ask? Well, let me go back to this for a moment. See, right here I've got delta V1 and delta V2. And I don't care about the delta U2 and delta U1, because that's for the bitangent. I only need to calculate the tangent, so I'm just using delta V2 and delta V1. So, if you know matrix math, the way this would work is pretty simple. Delta V1 times E dot get x minus delta V2 times E dot get x minus delta V1 times E dot x. So yeah, that's how this is going to work. Just thought I'd show you, just because I thought how we're sort of cutting out part of the matrix math might be a bit confusing. So yeah, I'm going to take edge 1 dot get x, and I'm going to multiply delta V1 times that, and actually, yeah, thought I screwed that up, times delta V2, be careful about that, and yeah, just from there I'm just going to subtract delta V1 times edge 1 dot get x. And really, I screwed something up, didn't I? And yeah, I did my mental matrix math slightly wrong. Remember, it's row to column. So this would be V2 and E times E1 dot x, and negative delta V1 times E2 x, because remember, row to column. So yeah, this should be edge 2. And the nice thing is, since we're calculating the tangent, this sort of just goes down the line. We need to do the exact same calculation, except with... Wait, not edge... except with y and z rather than x. And there, that gets us the tangent. But, here's the thing. More than one Oh, this should be get z. Yeah, don't do whatever I just did. That's not good. And you can expand that out, I guess. Sure, why not? And yeah. But as I was saying, one thing you gotta be careful of here. More than one vertex can share... triangles can share vertices. One vertex can be part of multiple triangles. So although this tangent might be correct for whatever triangle it's that the vertex is part of right now, when calculating another triangle and the same vertex comes up, I might be trying to get a different tangent, and then what do? So the solution, just like with normals, is to average all the tangents for the vertex, and then interpolate them. And that'll get you sort of a nice well, they'll get you proper tangents, because they're interpolated and whatnot. Yeah, I was just giving a nice, smooth interpolation across the face, and getting you what it should be in sort of the simulated... Well, no, it's interpolating the tangents, okay? I don't know what I'm trying to talk about now, but yeah, we're interpolating the tangents. So what I'm going to do is I'm going to take the tangent that already exists, which I don't have yet. So that'd be kind of important. I'm going to create an array list of tangents, just like the array of normals, except, well, it's for tangents. And yeah, I'm going to do something pretty much just like I was doing with normals. I'm going to, in fact, just copy and paste the code for sort of the adding up. The only difference is I'm going to replace it with tangents. And there. And of course I'm going to add the tangent, not the normal, but that's all there is to it. Final thing, just like when I went here and went through all the different tangents and normalized them so they'd be length 1 and effectively doing the average, well, you know, doing the part of the average where you're dividing by the total number, yeah, that's what this is doing. It's just easier with vectors because it's normalization and what. I'm just spewing nonsense today. I'm sorry. I'm just trying to say way too much at once. Sorry about that. But yeah, we're going to go through all the tangents and normalize them so that we don't have tangents that are different length based on vertex sharing. So yeah, and that's all there is to calculating the tangents. And there. However, there's still one more trick to calculating tangents in model loaders that I want to show off. So, right here I have my function that's converting my OBJ model, which, as you see, isn't storing any tangents, they need to be calculated, and it's converting it to the indexed model, which is sort of, well, the format which has all the position, texture coordinate, and normal and tangent data. So, what you need to do, or what you probably want to do, is when you're setting up your indexed models, you want, of course, just start with a tangent. Start with a default tangent. You don't want to calculate, kind of like I'm doing with normals. I'm not really calculating a normal, I'm just adding sort of a default one. So, oh, and I want to create a getter for tangents. So, yeah, I'm going to copy the getter for normals and say get tangents, which returns tangents. There. So what I'm going to do is I'm going to start by adding a default tangent. It's going to be just new vector of nothing, because we haven't calculated them yet. I'm going to do that for both of them. So this is just so there's something there to actually calculate on. Now at the end, what you want to do is you want to calculate the tangents. Now, should you use the result mesh or the normal model? And you're probably going to want to use the normal model in this case, the one with all the smoothed, well, you know, the smoothed faces and whatnot. Because otherwise you're going to get tangent seams, and that's just going to look really awkward, and yeah. So you want to calculate the tangents on the normal model, and then map them back to the result mesh. That's critical here. You need to map them back, just like this loop right here is mapping all the normals back to the result mesh with an index map. In this case, well, it's a map in this case, but yeah, you know. Yeah, you need to map them all back. So, yeah, gonna do the same thing here. Gonna get tangents, and I'm going to add, and the reason I'm adding is because it's 0, so should just be nothing by default. I'm going to add the normal model.get tangents. I'm going to get it at the mapped index. And that really is, that's all there is to calculating tangents in a model loader. Just, you probably want to do it in the smoothed model. In this case, it's the normal model, because that'll prevent you from getting tangent seams. And you're going to want to map the smoothed vertices, or smooth model tangents, back to your final mesh, just like with normals, because otherwise you're not going to map to the correct vertices, and it's going to look really weird. So yeah, that's all I wanted to bring up. I'm going to actually run this just to be sure I haven't screwed something up in all the code here. And, oh, I forgot to calculate tangents. That's going to be a problem. Yeah, right here, make sure you're calculating tangents, not getting tangents. Yeah, that's kind of important. And yeah, I'm going to run one last time just to be sure that nothing screwed up. And there. I haven't implemented normal mapping in this, but that should give you an idea of how you can actually get tangents working if you're not using a model loader that has tangent calculation for you. And yeah. So, the last piece of normal mapping related math I want to talk about is the Gramm-Schmidt process. And this isn't strictly related to normal mapping, but normal mapping is a case where it's exceptionally useful. So let's say you've got a normal and you got a tangent, and they look something like this. They're almost right, but they're just not quite at the 90-degree angle that they should be. And if you could try creating a rotation matrix out of a normal and a tangent like this, the normals are going to be facing in slightly the wrong direction, and it's going to look a little bit weird. And, it's just not quite going to be right. So, if you're in a situation like this, it might seem like, well, why on earth would this ever happen? But when you're interpolating normals and tangents, there's going to be slight errors like this, and it's going to make your normal mapping look not as good. It's going to be slightly off. So how can you correct it? And the answer is the Gramm-Schmidt process. Now what this does is it reorthogonalizes two vectors, or in non-math nerd speak, it puts them at a 90-degree angle between them. So, yeah. And here's how this works. First thing you want to do is you want to make sure they're normalized. They should be normalized. Well, actually they won't be if they're being interpolated, but so you want to normalize them anyways, but yeah. You want to make sure these are normalized, because that's important. Why is that important? Because we're going to take the dot product. And the dot product, as you should know if you know vector math, it gives you the angle between two vectors. So, well, or the cosine of the angle between two vectors. So, if these are at a perfect 90-degree angle, this should return 0. If the normal and the tangent are exactly the same, this should return 1. If they're like, I don't know, the normal's going over, there's like a 45-degree angle between them, it should return the square root of 2 over 2, etc., etc. It's the cosine you know and love. That's great. How's that going to help us reorthogonalize things? Well, here's sort of the trick. What happens if you multiply the normal by the cosine, by this dot product here? Well, it's already normalized, so the length of the normal will become this sort of cosine. And it'll end up looking something like this. And hopefully you start to see how this is going to help us reorthogonalize, because what's this line between the endpoint of the tangent now and the normal? Well, that's the new orthogonalized tangent. And that's sort of the trick. You take the dot product between the normal and the tangent, you scale the normal by that, and then what you can do is you can take the tangent and subtract that value. And the reason that works is because if you know vector math, if you take a point and subtract it from another point, well, it gives you the line towards the original point, So in this case, we're taking the tangent, subtracting this scaled down normal, and it's giving us the line between that scaled down normal and the tangent. And that's all there is to it. So if you use this new tangent, you get normal and a tangent looking like this. Perfectly orthogonal, perfect 90-degree angle between them. And when you create a rotation matrix out of this, you're going to get proper rotated normals and not have any wonky, slightly off bump mapping. So yeah, that's the Gramm-Schmidt process, and that's how it can help normal mapping. And you can do this to reorthogonalize any two vectors, but it's just, again, a case where it's exceptionally useful. So yeah, and with that, that's really all the mathematics I wanted to talk about with normal mapping. So thank you, hope you enjoyed, hope you learned, and I'll see you next time. And one final thing. I went ahead and made the necessary changes in the 3D engine so that tangents actually are being stored in the mesh. They're, well, not really the line of code, sorry, but yeah, as you see, they're being passed to shaders, so yeah. I went ahead and did that for you guys, so if you want to use tangents for stuff like normal mapping, you can just download the Java engine and follow along without having to figure out how to add tangent support or how to load tangents and calculate tangents with the indexed model and such, so yeah, there you go. And I'll leave a link to that repository on GitHub. So, thank you, hope you enjoyed, and now I'll see you next time.